and now all we have to do is argue that to the n is exactly x. Right? How do you think we're going to do that? Well, we have this nice little lemma 4. So now to prove that the two possible, we do by contradiction. Or I'll do this time. By contradiction, we show that so if alpha to the n was greater than x, or there's something smaller that's still greater than x, so it's not the least upper bound by the lemma. If alpha to the n was less than x, well, there's something bigger that it to the n is less than x by the lemma, so it's again not an upper bound. So these cause a contradiction by lemma 4, and then we're done. So that proves there exists one. So I'm going to stop. And then I'm not done with the proof, turns out. But are there questions? That was fast. But this is just an outline. And my point is, look at these lemmas. I think you guys understood how the lemmas worked out. Try to go, if you can't understand this now, I want to move on to complex numbers. But if you can't understand this now, that's fine. Go look at it at home. Go think about it at home and compare these 4 lemmas and see where they fit in. And the proof is very straightforward. The idea is, it's just those 4 ideas just applied in order. Take the set you want, prove it has an upper bound, take its upper bound, prove its upper bound has the property you want. Simple three steps, and you do this for a lot of things. In fact, I think both 6 and 7, which are probably the hardest problems, they're not the hardest problems in the book, but they're definitely pretty hard problems. This is sort of the principle behind it. So he walks you through all the stupid proofs. Are there questions? I know this is very quiet. I feel like I'm just boring everyone to death, but I'm not sure. Yeah, well, whatever. So, but you guys at least understand the big idea. You show it has to have the property you want because of the lemma 4 we showed it has to, or else it wouldn't be the supremo. So you argue alpha wouldn't be the supremo if it had either of these two things. Cool. So here's my last question. Are we done? This is like test taking skills. You go through this horrible proof on the test, let's say, or on a quiz, and then the proof won't be this horrible on either probably, but you go through some proof. You just move on. You should always first check, did I really prove everything I was asked to prove? Have I proven everything I was asked to prove? What am I missing? And I know it's just an exclamation point, but I said there exists a unique y. I showed you there exists a y. I didn't show it was unique. But actually, that's why I haven't used lemma 1. Lemma 1 gives you uniqueness for free. It says if you have 2 different numbers that are positive, their nth power is different. So can anybody else have the same nth power? No. So actually, lemma 1 gives you uniqueness. See that? So with lemma 1, we get uniqueness, and then lemma 2, 3, and 4 are doing like a bunch of calisthenics. We get or actually, technically, we only used lemma 3 to prove lemma 4, and we only used lemma 2 once to show it was not empty. Okay? So honestly speaking, do you guys think you could sit down with Rudin and maybe make sense of his proof now? After seeing like most of the steps laid out in detail and explanation of how they fit together. That's like your mini homework. These are the simple things. I'm not going to put something like this on the quiz. I may ask you about this proof, right? I might make you use this somehow in a very small, like 2-line proof or something. But I'm never going to ask you to do something like this on a quiz. So don't worry about that. I only do these in class just so you get kind of used to the feel of things. Eventually, I hope. Or at least I eventually thought these were cool. Originally when I saw them, I thought they were like the biggest nightmare ever. But then you just, after a while, you realize there's certain elegance to being able to, because everyone can tell you, like this lemma, for instance, everyone can tell you, I got some t such that t to the n is less than 5. There's got to be some number bigger such that to the n is still less than 5, right? You can say that, but now you actually see how the idea to prove it. And I think that's interesting. At least that you can do it with like such bare bone methods, just like a lot of computation. Are we good? So you guys now are happy with everything that is reals, I suppose. So actually, we will finish Rudin's chapter 1 today. So I plan on starting 2 tomorrow for sure, but the question is whether I give you guys a small introduction to sequence. So the only thing I don't like about Rudin is he does sequences after chapter 2, and then it turns out you can do all of chapter 2 with just sequences instead of doing it the way he does chapter 2. So I might introduce sequences. I'm still like having like a existential debate with myself in my mind. So I'll let you know how that goes tomorrow. But definitely we're going to start into chapter 2 and get through basic definitions. Great. Are we happy? All right, so now let's take a quick break before, not like a real break, but we're going to take a mental break by looking at something very simple. And this is something you saw on the worksheet. It's called the extended reals. I just want to state this just so you guys know what it is, but it's no big deal. This is just trying to make, so this is basically what you do is you take the real numbers and you add 2 points. The points are going to be infinity and minus infinity. So, so this is what we'll call the extended reals. So we call the extended reals. And extended reals. Where ow, oh my god. X, for any x in R, x is always less than infinity and always greater than minus infinity. So so this is just making technical something you guys already could have figured out. The only reason we care about this is now every set is non-empty set is bounded above. And every non-empty set is bounded below, right? Positive infinity is an upper bound for everybody. Negative infinity is a lower bound for everybody, right? So the reason we care about this is, the only reason I'm saying this is what he says in the book. The only reason we care is that when I say this, you can say like, for instance, I could give you, what's the supremum of z? Well, under the what I've said before, this doesn't make any sense. It's not bounded above. But now it is. So now we could define the supremum of z just to be this infinity under this framework. Does that make sense? So when I say find the supremum or infimum in the extended reals, I'm just saying find the least upper bound, and you can say infinity and minus infinity if that's the answer. Does that make sense? That's all the extended reals mean. Nice and easy. So this is something you've always, when you did limits in calculus, I'm sure you guys know the limit's infinity, the limit's negative infinity. You guys said that. That's all. That's just making somewhat. So he has this whole section on it. This is making somewhat rigorous that idea. Does that make sense? Cool. It's not even really that rigorous. Okay. And the other really small thing that I expect everybody has already done, but I'll say it anyway, is I want to define Euclidean spaces, which is just a fancy word for something you've all done. And then we'll move on to C. So definition. We define the set RK. Oh yeah, by the way, this was also really funny. I'd already taken a bunch of classes, and I did one of these things called an RU. I don't know if any of you have ever done an RU, but it's like a research experience for undergraduates where you go and like learn a lot about something you're never going to talk about again, and then pretend to do research in it, and then get paid. That's the good part. You get paid to do it. But I had to read all these papers that kept saying Euclidean space, Euclidean space, Euclidean space. Now I knew what Rn was, or Rk was, right? But I was like, kept getting confused. So if you ever see the word Euclidean space, it means Rn for some n, or some k, or whatever. For any natural number to be, and I mean, I know you guys know this, but the set x1 through xn, or xk, the way I'm writing it, such that xi are each real. So right, it's exactly what you expect. These are the set of all n tuples, or k tuples, of real numbers. And you guys hopefully have all taken some sort of linear algebra, so you know this is a vector space, and all this stuff. But to summarize this space has the property that with the following definitions, with x, y, and rk, alpha and r. If you define things like this, I'm sure you all know this, x1 plus y1, xk, y plus yk. And then alpha x to be alpha x1, alpha xk. So you guys already know this, but you know that if we define this, it's a vector space. But this, RK is a vector space. Right, and so I just wanted, I'm only writing it down so you all know that.